Hello, you're welcome to this physics lesson in which I'll talk about the Wheatstone Bridge and the METRE Bridge. I am Mr. Kugonza and my email address is apkugonza@gmail.com. The Wheatstone Bridge circuit is what you see on the screen. It is named after the scientist that designed it. He was called Wheatstone and he did this in 1843. And it is used to determine resistance over resistor accurately. This is one method of determining resistance accurately. So what we see is four resistors, R1 and R1, R2, R3, and Rx. And Rx is the resistor of a known resistance. So we would like to find that resistance. So we can determine it if we connect these resistors as shown in this diagram. Now, when a current flows from the battery, that current splits at point A, and part of it goes to R1, some current goes to R3. But when R2 is adjusted, at some position or point, there will be no current flowing through the galvanometer. So the potential difference across R1 is the same as the PD across R3. Similarly, the PD across R2 will be the same as PD across Rx. And also the current that flows through R1 and R2 will be the same when no current flows through the galvanometer, while the current flowing through R3 and Rx will also be the same. Maybe another thing to note here is to know that R1 and R3 are actually two resistors in parallel, whereas Rx and R2 are also resistors in parallel at the balance point. So following those conditions that I have mentioned, we can therefore determine the balanced condition of a Wheatstone bridge. PD across R1 equal to PD across R3, PD across R2 equal to PD across Rx. Write down the equations of following the currents that pass through them and get the balanced condition. So using this balanced condition, with only Rx as the unknown resistance, we can determine its value. Wheatstone bridge is not suitable for measuring very low or very high resistances. When the resistance is very low, it becomes comparable with the resistance of the connecting wires, and this will cause inaccuracies in determining the unknown resistance. When the resistance is very high, the current becomes very low and the galvanometer becomes insensitive to such low current. So for that reason, we don't use it to determine very low or very high resistances. Let us look at this question here. The diagram on the next slide shows resistors arranged to form a bridge circuit. Calculate the value of X for which the galvanometer shows no deflection. The value of P, Q, R, and S are given. We can look at them from here, from the diagram. 500 ohms for P, 800 ohms Q, 1000 ohms S, and R comprises of two resistors, 400 and X. Now, we need this, since these two resistors are in series, we add them to get the total resistance. Now, we use the balance condition in order to solve this problem. P divided by Q is equal to R over S. We don't need to know the EMF of the driver cell. As long as it is mentioned that there is a balance condition, that means no current flows through the galvanometer. So we are not going to use Kirchhoff's laws in order to determine that unknown resistance. So substituting in that equation, we get the now known value X as 225 ohms. Now, let us talk about the METRE bridge. METRE bridge is a form of a Wheatstone bridge. It consists of a uniform resistance wire, which is 1 meter long, and it is connected to thick copper strips. So the copper strips that it consists of are these, which are shaped, this one on the left-hand side, shaped like letter L, inverted, and also on the right-hand side, those are copper strips. And in the middle, there is one which is horizontal, where there is point B. Those are the copper strips. They have a gap in between. They have gaps in between them, and on the left hand side the gap, a resistor R is connected in that gap, and on the right hand side a resistor S is also connected to the gap. We have a galvanometer and jockey, which taps along the uniform resistance wire that is 1 meter long, strictly 1 meter, because even the bridge itself is referred to as a meter bridge. So the wire AC is 1 meter long, or 100 centimeters. So for that reason, if at balance the length from A to D is L1, then the remaining length from point D to point C is 100 minus L, because the total length of that wire is 100 centimeters. So this bridge circuit is connected to a driver cell, and we have a plug key in this diagram, but the switch can always be any other type of switch. We can also have a switch that is not necessarily a plug key switch. So current flows from the driver cell, reaches point A, and then it splits into two. Some current goes through the copper strip to R and S, while some current flows through the resistance wire. And then at some point we are able to determine the balance condition. So in order to derive the balance condition, we look at the diagram from this angle. Let us label all those currents. Suppose the current that goes through the copper strip is I2, and the current that passes through the wire is I1. At the point when the galvanometer shows no deflection, there will be no current which flows through it. Therefore, the current Ig through the galvanometer is 0, and so the same current that passes through R1 is the current that passes through R2. Now, and also the current that goes through AD will continue up to point B, the same current I. So in order to get the balance condition, we notice that the potential difference across R1 is going to be the potential difference from point A up to point D. Now, supposing that this is a uniform resistance wire whose resistance per centimeter is small r, if small r represents the resistance per centimeter, so the total resistance from point A to point D is going to be that small r times L1. Now, when you multiply that by the current I1, we get the PD from A to D. So that PD is going to be equal to the PD across R1, which is I2 times R1. On the other hand, also, if we multiply current I1 by small r times L2, we get the total PD from point D to point B, and that PD is equal to I2 times R2. So using those equations, we therefore be able to determine the balance condition. So those equations are what you see on the screen. Most of this I have already explained. So once you have the equations, equation 1 and equation 2, all you do is to divide those two equations, and you get the balance condition of a Wheatstone bridge, which is R1 over R2 is equal to L1 over L2. So one part of the balance condition for a meter bridge is a ratio of resistances, while the other is the ratio of the length. So please take note of that. And also note that the length L2 is 100 minus L. So we can as well write that equation as R1 over R2 is equal to L1 divided by 100 minus L1. So this is the derivation of the balance condition of a meter bridge. Meter bridge has two applications, only two applications. One is determining the resistivity of a wire, and the other application of the meter bridge is to measure the temperature coefficient of resistance of a material. Those two terms are all not new. Resistivity of a wire we have already discussed in our earlier discussion, and also the temperature coefficient of resistance. But we are going to see how the meter bridge is used in determining each of these two quantities. If we would like to find the resistivity of a wire using a meter bridge, we connect that wire, a specific length of that wire in the left-hand gap of that meter bridge, and in the right-hand gap we connect standard resistor that is shown in that diagram as RS. So starting with the length L equal to 10 centimeters, the jockey is tapped along the wire until the galvanometer shows no deflection. The balance length L1 and L2 are measured and recorded. Or you can actually say they are read from the meter bridge wire, because there is a ruler underneath that meter bridge. So you can read the balance length and record those values. Then the resistance of the wire is calculated from that point. That's using the condition, the meter bridge condition. You get the resistance of the wire that is connected in the left-hand side. Then the experiment is repeated when the length of the wire is between the gap, in that gap is 20, 30, 40, and so on. The value Rx is calculated for each of those different distances, and then you tabulate the values. You draw a table and put all your values in a table, including values of Lx, L1, L2, and Rx. You plot a graph of Rx against Lx, the length of the wire. That graph is going to give you a straight line graph, and then its slope is also determined. Then you determine the diameter of the wire using a micrometer screw gauge at 3 different points and calculate the average value. Once you have the average value of the diameter of the wire, then lastly you find the resistivity of the wire by the expression that resistivity is equal to the slope times pi d squared divided by 4. So that is how you find the resistivity of a wire using a meter bridge. Now, how can we find the temperature coefficient of resistance? So this one, we connect a wire, wind a wire on a piece of wood and immerse it in water, which is in a beaker, and then place that water on a tripod stand, underneath being a Bunsen burner, and then connect the other ends of the wire to a meter bridge. On the right hand side, you connect a resistor, standard resistor. The other components of the meter bridge are already explained. So the procedure for determining the temperature coefficient of resistance is this. The water is heated to a certain temperature. After thorough stirring, the temperature is read from the thermometer. The jockey is tapped along the wire until the galvanometer shows no deflection. The procedure is repeated with increasing values of temperature. The results are tabulated including values of R theta. So in other words, you're finding the resistance at a specific temperature. A graph of R theta against theta is plotted. A straight line graph is obtained and the slope of that graph is determined. The temperature coefficient of resistance between 0 and theta degrees is going to be equal to the slope divided by the resistance at 0 degrees. So that is how we determine the temperature coefficient of resistance of a wire. Thank you very much for listening to me. This is the end of our lesson, and it's also the end of this topic, current electricity. I hope you have enjoyed my online lessons. Goodbye.